All right, good morning, everybody. So today we're going to use logarithms, and you can see in this formula it's a natural log. So we're going to use formulas that are already given to us. So we're going to apply what we know about logarithms to solve new and non-routine problems. And some of these formulas I have never used myself before. For example, Newton's law of cooling. This equation, you could use this like if you're like a crime scene investigator, you could use this to calculate the time of death. I've had no reason to do that as a teacher ever, luckily. But so some of these are going to be new for both you and me. But I do know how to use a formula, and we'll walk through them. This is the notes, and it is the practice. So whatever we don't finish, I'll have you finish yourself. So the first thing, which I think is probably the coolest thing on the page, is Newton's law of cooling. And here's the formula. Here's what each thing is. What helps me a lot, is to kind of label in what everything is. Like this is your second temperature. S, that's your environmental temperature. Like that's the room temperature. We'll just call it room temp. And then T sub O, anytime you have, I should say T sub 0, that's initial. So this is the initial, so the first. Little t, that's time. And K, this is your constant. So when you're solving these, the first thing you want to do is you want to find that constant. So here's an example. So you're on the police force, and you find a body in a hotel room at midnight. The temperature in the room was 60 degrees Fahrenheit. So that means S is going to be 60. That's why they put S as 60. The body temperature at that time was 80 degrees. So that'd be initial. So we initially start with 80 degrees. So T sub O is 80. At 2 a.m., so you found it at midnight, and then 2 hours later, so that the time is going to be 2 hours later. The second body temperature, that'd be this T, is 75. And then they also tell us normal body temperature is 98.6 degrees. So we're going to find the time of death. So they helped us out. We had 2 hours of data. This is the temperature now. This is the temperature it was 2 hours ago. S equals 60. That's the room temperature. That's kind of cold, I think. So now we could plug in. So first we're going to find K. So we're going to say K, T, remember T is 2, equals the natural log of T. T is 75. And you subtract off the room temperature. And then T sub 0, that's what it was initially. So initially it was 80 degrees subtracted by room temperature. So here's all that's going on. We're trying to find our K. This is 2 hours have passed. The temperature of the body started out at 80 degrees. 2 hours later, I measured it. It was 75 degrees, and the room temperature was 60 degrees. So really, I just need to divide all this by 2. and that'll tell me my K value. So I'm going to type that in the calculator. Scientific, most likely. And so I got natural log of 75 minus 60 divided by 80 minus 60. Close it all off, divided by 2. And notice my K value is approximately negative 0.1438. So that's my K value. That's my constant. So now that I know K, I can plug that here. I know my K. All right, so now we're going to use this information to work backwards. So we worked forward before, now we're going to work backwards. And the way we're going to work backwards is the body started at 80 degrees, went to 75, but normal body temperature of a body is 98.6. So we could go from 98.6 to 80 and see what happens. So in other words, this is going to be 98.6, the initial temperature, approximately. Not every person's the same. And then this is going to be 80 degrees. So we're going to work our way backwards. We'll know what K is now, and we can use K to find T. So we're going to work backwards here. And then the room temperature, of course, is still going to be 60 degrees. So plugging in, I would say, okay, K, which is negative 0.1438 times T, which we don't know what T is. And again, I'm using this formula. We know our K now, find T, and I'm going to put natural log. And this time, we're going to let the initial temperature be 98.6 degrees. And we're going to find how long it took to go from 98.6 degrees to that initial finding of 80 degrees. Subtract off the room temperature. And then I'm just going to punch all this in the calculator. So if I divide both sides by negative 0.14384, I get T equals the natural log of 80 minus 60 all over 98.6 minus 60 divided by my K, negative 0.14384. So I'm solving for T. So I'm going to punch that in the calculator, see what I get. Which I might just play around with this one. It's almost done. This time it's 80. And it started out at 98.6. And this time we're trying to solve for T, so I'm dividing by the K value, which was negative 0.14384. And I get T is 4.57. So what does that mean? This could end up being seconds, could be minutes, could be hours. Hours is hours because that's how we measured it initially. I have seen this where T is minutes, but from the very beginning, we talked about hours. We started out at midnight and we worked to 2 a.m. We let T be 2. Had we let T be 120 for minutes, then this would be in minutes. So 4.57. You can't have 4.57 of an hour. So we know this is 4 hours for sure. 4 hours ago. And then if you take 0.57 times 60, that's how many minutes. So 0.57 times 60, that's 34-ish minutes. So you could use this to say that initially the body was found at midnight. So if you take midnight minus 4 hours, 34 minutes. That would be the time. So let me think. Midnight, take away 1 hour, 11, take another hour, 10, another hour, 9, another hour, 8. So now it's 8 o'clock. Take away 34 minutes from 8 o'clock. That's 7 hours and it's too early in the morning. 7 hours and 26 minutes. So it'll be 7:26 p.m. Let me make sure. Yes. Okay. So using Newton's law of cooling, I determined that I calculate about 7:26. Okay. Any questions so far? All right. In this little packet, I may not have you do all of them. There's quite a few, but there's another one just like this. The very last problem, I think it is. Number 11. If you want to try yourself later. Okay. But really, the skill is, this is probably more advanced than what you guys need to know. The skill is that you can plug into an equation and solve. And Newton's law of cooling is actually pretty intense, I guess you could say. Let's go to number 2. On a college campus of 5,000 students, one student returned from a vacation, almost said vaccination. One student returned from a vacation with the contagious 3-day flu virus. The spread of the virus through the student body can be modeled by, where Y is the total number of infected after T days. How many students will have been infected by the end of 5 days? Okay. So 5 days. And I have to read this. So that's always 5,000, probably because there's 5,000 students. That's always a 1 plus 4.999 they must have found. E is approximately 2.713. We'll plug that in the calculator. T days. So they want to know how many students have been infected by the end of 5 days. So we know that this T, we're going to put in a 5. How many students? Well, Y is the total number of students. So really all they're asking me to do is take this and plug it in and see what I get. Is that negative 0.8 T? Actually, let's go look at the graph. And I'm going to leave this as a T. I'm going to change it to an X so I can graph it. So I'm going to type that into Desmos. All right. So we had 5,000 divided by 1 plus 4.999 e to the negative 0.8 x. It doesn't make sense for negative time, so I almost need to go up to 5,000 first. You can see it's like it has a horizontal asymptote at 5,000, never quite gets there. And I was wrong. We don't really need to go to 5,000. Oops. But it doesn't make any sense to talk about negative people. So we'll start with, you kind of see what's going on. I'd prefer just seeing a table myself. So I'm going to go here and hit table. And so initially, that would mean what, 833? So That doesn't make any sense. You would think that after initially it'd be 1. Must have typed something in wrong. Or maybe their equation's wrong. But really all they wanted us to do is go here and type 5 in. And according to this, which I don't necessarily agree with their equation, after 5 days, there would be 4,580 people infected. It honestly doesn't make sense. Okay. We'll just go with their equation. I don't agree with their equation. That doesn't make logical sense there. All right, we'll go to the next one. Hopefully this equation works. So in other words, plug 5 in here and you get 4,580 people infected. All right, for 1970 through 1990, the median age A, so median age A of Americans at their first marriage can be modeled by the 2 equations. This one's for women. This one's for men. Somebody came up with these equations. They may not even be real equations, just based off the time. So T represents 0. T equals 0 represents 1970. So we're going to find the median age of women and men at their first marriage in the following years. So first, 1970, T equals 0 represents 1970. So what I need to do is I need to plug 0 in here and 0 in there. Okay, so I'm going to plug in T equals 0 into both. And I'm going to find woman and men. 1980, well, if T equals 0 is 1970, 1980 would be 10 years later, so T equals 10. And I'm going to find the median age of women and men. And then 1990, from 1970, if that's times 0, that'd be 20 years. Woman. I can't write today. So I'm just going to change this number. I'm going to put 0 here, 0 there, then 10, then 10, then 20, then 20. This 100% would be way easier with the graph. So I'm going to go type in women first. Let's start with women, which would be this equation. Get rid of this. So the woman equation is you take 20.4, you add on 3.1, divided by 1 plus 43 e to the negative 0.36, and instead of t, I'm going to use x. Okay, make sure I type that in correctly. I didn't put negative 0.36, but that's the same thing. And then I'm probably just going to go to a table. So here's t equals 0, 20. Okay, so around 20 years old, 20 and a half. Then we wanted to find when t was 10. That's 21.82. And then we go to 20, and that's 23.40. Okay, so that's about the age. That would be the age of women on average, or I should say the median age. For men, I have to type it in. The equation was slightly different. It was 22.4 plus 3.1 divided by 1 plus 63 e to the negative 0.36 t, but instead of t, I'll put x. Go look at my table. So at 0, it was 22.4. We'll say 22.45. 10 years later, 23.54. 20 years later, 25.36. I think it's a lot easier to plug in that way versus writing down every single equation. Now here's what I have. In 1970, the median age of women was around 20, and for men, 22. 10 years later, according to this equation, the median age for women was 21, for men, 23. And then 1990, it would be 23 and 25. Next, the number N of bacteria present, so this is bacteria present, in a culture at time t, or t's in hours, so that's hours, obeys the equation this. After how many hours will the population equal 1,500? 2,000. So we want to know, when does N equal 1,500? So we have to solve that to solve for t. If you wanted to, you could use natural logarithms, take the natural log of both sides, or you could type this in and see where they intersect. For time, I'm just going to type it in. So I'm going to type in 1,500 and see when that intersects this. So we got 1,500. We're trying to see when there's bacteria of 1,500. And the other side was e to the 1,000. 1,000 e to the 0.01x. And then we can just look to see where they intersect. Uh, 40.55. Remember, T is an hour. So we'll say in 40 hours, 40 and a half hours, there will be 1,500 bacteria. How about 2,000? That was the next question. So when does this equal 2,000? So I just need to go and look for 2,000 now. So when is this 2,000? And again, you could solve algebraically. Just for time, I've decided not to. 69.315. So after 69 hours, that's when we have 2,000 bacteria. So like a lot of these equations I've never seen before, but I know how to plug into an equation. So that's really the skill. I give you an equation, can you plug in? This is another one of those room temperature problems. I'll let you do that one yourself. This is about a spacecraft. There's a lot going on. V is velocity right here. T, what is T? So the rocket's maximum velocity is v, kilometers per second, that'd be t, about t seconds. And so you just plug in, that one is a little bit tricky. Just try your best on that one. 7 you should be able to do from last class period. If you have $5,000 and it pays 8% interest compounded quarterly, how much time before you have 6,000? We did that last class period. Number 8. Number 8, you guys are not ready for. We'll cross off number 8. The Richter scale for earthquakes. They tell you how to plug in. Okay, so find the magnitude. So find the magnitude here. Sound intensity. And then another Newton's law of cooling. So on this, just try your best. I don't expect perfection. I know some of this is brand new for all of you. I just want you to know that there are equations out there that you can plug into. On the district assessment, you will be given an equation and they'll tell you what numbers to plug in, and all you have to do is plug in. So that's really the skill for today. Other than that, I don't think I have time for another problem. I will be on office hours if you have any questions. I'll see you later. Bye-bye.